All right, here we go. Monday, starting a new week. All right, we are in it with circles. The remaining parts of the chapter, every single day, we'll get multiple facts, theorems, definitions, and we're gonna get formulas. We won't see if we'll get results again today, but we're gonna get formulas starting tomorrow on Tuesday. If you need to take a practice day because it's a bit too overwhelming, all the formulas, we can absolutely do that. Make darn sure, I mean, the test is going to be next week, but make darn sure we don't get to the test day and you're like, it's just a bit too overwhelming. I need an extra practice day. Just ask for one, be happy to give it to you. All right, here we go. Here's your homework. Okay, today deals with arcs and chords. We're familiar with one of those words. We've probably heard of the other word, but you're going to be intimately familiar with both arcs and chords at the end of this lesson. All right, so let's do a quick review of what we know so far. Well, let's see. I've got a circle there, circle O. I've got chord RS. I've got points TR and S. What else do I have? I have the arcs. Remember from last lesson, arcs. So I have lots of arcs there. I'll just give you two of them. So the red one there is minor arc. Remember, minor arcs are arcs less than 180 degrees. So I have minor arc RS, and then I have major arcs. Remember, major arcs are more than 180 degrees. So for instance, TRS. Remember, major arcs have to have 3 letters. Minor arcs get 2 letters. All right, we also had this idea that if you have a center of a circle and from the center you make an angle with 2 segments, that angle is called the central angle. It's in the middle, makes sense. And then lastly, the arc that central angle creates, we're talking about the red arc right there, is equal in measurement of how much of the circle it is, measurement of degrees, it is equal to the central angle. So 50-degree central angle, 50-degree minor arc right there. All right, so that's called the arc measure. Remember I said eventually, the end of the chapter, we're going to get arc distance. That's literally how many inches, centimeters, whatever your units you choose to use, the distance of that arc. But for right now, we're describing that red arc, the minor arc YZ, in terms of how much of the 360 degrees it is. The rest of the chapter, it can be absolutely challenging. Just be ready for it. Here we go. So let's do a proof. We haven't done a proof in a while. So let's see, I got a circle O. Looks like I got 2 chords there, TU and RS. And my given says that those 2 chords are congruent. Oh, I'm sorry, I'm saying this backwards. We will get the inverse of this or converse of this as well too. But I'm given the 2 red parts are congruent. So the 2 arcs that the 2 chords produce. So the chords TU and RS form or cut an arc. That would be arc TU and arc RS, and we're given that the 2 arcs are congruent, so their arc measurements are equal. We're asked to prove that if that's the case in a circle, if 2 arcs are congruent, then the chords, if we connect the endpoints of the 2 arcs, TU, RS, then the chords are congruent. All right, so here we go. Well, you are in high school. It's geometry. How do we typically show that things are congruent? That's right. We make triangles. So I'm going to make 2 triangles. I'm going to connect points T, U, R, and S all to the center of the circle. So that means I'm constructing radii. So there's your circles. I'm also labeling angle 1 and angle 2. Now it looks, on just a brief look there, it looks like angle 1 and angle 2 are vertical, but they're not. They could be, but in this case, I'm not claiming that they're vertical angles. If you take those 2 triangles and you shift them around the triangle a little bit, you can clearly make 2 angles that are not vertical of each other. So I'm not going to use that in part of my proof. But what I am going to use is the fact that since I just made radii of the same circle, that all the radii are equal to one another. Well, the radius, or the radius doesn't change on a circle. All right, so cool. So I've got 2, and then my goal here is to show that the 2 triangles are congruent. So let's see, I've got 2 sides of each triangle now congruent to each other. If I could just show that angle 1 and angle 2 are congruent, well, I can, and here's how I can do that. notice that in our given, we're given that arc RS and arc TU are congruent. Now, if you look at just arc TU, well, it has a central angle of 2. And therefore, whatever the arc is, RS is the central angle, 1. And then do the same thing for TU. So arc TU would have a central angle of angle 2. And since the two arcs are equal, therefore the two central angles are equal. Therefore, I have an SAS, the two triangles congruent, and by CP/CTC, I can claim that chord TU is congruent to chord RS. And that's it. That's the proof. So let's see what we started with. We started with a circle, and we started with two chords that were congruent. I said it backwards again. Two arcs that are congruent. So if the two arcs are congruent, then their chords are congruent. And by the way, the converse of this works as well too. So this is theorem 9.4. It says in the same circle, and remember I said we would see this again frequently in this chapter. So it says in the same circle or congruent circles, that if two arcs are congruent, then they have congruent chords. And then I can say the converse, because the converse would be true as well, that if the two chords are congruent, then the two arcs. So this one is a biconditional if and only if, meaning that it goes both ways. All right, so I'll give you a moment to put that in your book of truth. Okay, just remember this is biconditional. It's an if and only if statement. So two chords are congruent, two arcs are congruent. Two arcs are congruent, two chords are congruent. All right. Oh, by the way, remember I said this chapter we get lots and lots and lots of formulas. Well, this is a statement. It's not necessarily a formula, but it's a statement. All right, here's an easy one. Look at the red point right there, point Y. If point Y is in the middle of arc, minor arc XZ, well, then we're going to call point Y an arc midpoint. Three statements, right? The first statement is Y is going to be the midpoint. This is a definition, not a proof. Y is going to be the midpoint of arc XZ. Well, that means it would cut that arc into two congruent parts. So now I have two equal arcs. Arc XY and arc ZY would be congruent. And then lastly, if anything goes through Y, including a radius or a diameter, then it would bisect arc XZ. All right, write that one down. Okay, another quick proof. All right, now this is the shape you need to lock into your head. So it looks like an upside down cross. But let's see how it's formed. It's formed from either taking, this is drawn as a diameter, but it could be a radius, either a diameter or radius that cuts a chord and creates an angle that's 90 degrees. If that's the shape you get, we're about to prove this, then it turns out that that radius or diameter cuts the chord in half and it cuts the arc. That would be arc AB in half. All right, but it's got to look like this. So the key point here is that 90-degree angle. That's the thing. That's the given. So if that shape, the cross is there, and the angle is 90 degrees, then it cuts the chord in half, and it cuts the arc in half. That's arc AB. All right, and if it cuts the arc in half, then you make two congruent parts. Okay, so let's see how we can prove this one. Same as the previous one, right? You're in high school. It's geometry. Let's make some triangles. Show that the triangles are congruent. Call out CP/CTC, and we're kind of done. That's half of the proof there. So let's see. So I'm going to construct from O to A and from O to B, and I'll label angle 1 and angle 2, kind of like the previous proof. Well, that means that the radii are congruent, and it also means that I have right angles. Now, the right angle comes from the given CD is perpendicular to AB. And if I have one right angle, I have two right angles. So AZO and BZO are both right angles. All right, so that's just the definition of perpendicular lines. The two radii are congruent, and OZ would be reflexive property. OZ is congruent to OZ, and the two radii are congruent. Okay. So let's see, do I have enough to show that two triangles are congruent? Let's see, I have the radii are congruent, and I have the reflexive property, and it's a right triangles. So by hypotenuse leg, the two triangles are congruent. Therefore, AZ is congruent to BZ by CP/CTC, and I've got on the statement there, I got that angle 1 is congruent to angle 2 by CPCTC. I'm going to use that to finish off the proof here. If you look at what I have to prove, I'm halfway done. I just now need to prove the two arcs AD and BD are congruent. And that's why I'm calling up angle 1 and angle 2. Okay, so let's see. If angle 1 is congruent to angle 2, those are both central angles to their respective arcs. And so the respective arcs are AD and BD. Therefore, they are also congruent. And that's how the proof ends. All right. So let's write this one up. This is theorem 9.5. Remember the construction. So the construction is you got a cross. And where the radii or diameter intersects the chord, it intersects at a right angle there. And if that's the case, then it breaks up the chord in half and it breaks up the arc in half. All right, so if we have perpendicular lines there, then the chord is cut in half and the arc is cut in half. Now it says AZ congruent to BZ, but that's the idea. Oh, sorry. All right, put that one on pause, write that one down, and let's move on. All right, lots of statements today, lots of statements. So what is homework problems going to look like? Some of them will get really, 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 really messy. All right, so this one looks a little overwhelming at first, but if you take little pieces, parts of it, it's not too bad. So let's see what we got here. Let's see, I see an arc there. Its measurement is 86. I don't have a central angle. I see a chord there of 10. And then, I got that cross-looking shape there. And I got a right angle. And I know from the previous theorem that that would cut that chord in half. Well, half of the chord is marked at 5, so that means the other half is also got to be 5. That's by theorem 9.5. So therefore, x must be 5. Now, how do we figure out y? Y is I don't have any central angles there, and y is a chord, or sorry, is an arc. I can't get my arcs and chords straight today. All right, so let's see. AB is, we just figured out 10. Why? Because it's already marked 5, and the other side, x, we just figured out is 5. 5 plus 5 is 10, and now we have congruent arcs. Oh, my word, I just said it again. Now we have congruent chords. Notice the EF is 10 and AB is 10. And if that's the case, if you have congruent, let's make sure I get it right. You have congruent chords, then the arcs are congruent. So that means EF, now be careful, and AB are congruent. So if EF is 86, then AB is 86. But I don't want AB, I want BD or DB. And we've got that cross thing again. And we know that if that's a right angle, then it breaks the arc in half. Therefore, Y would have to be 43. Okay. So most of these just require, I don't know, I find these fun and challenging. They're not too challenging in the sense of you get stuck, but they're also not so easy that doesn't require much thinking. So these do require a little bit of thinking and planning and picking out which one you want to solve for first, X or Y. All right, here's one with no picture, just words. These are by far the most challenging ones. So it says, find the length of a chord. All right, I'm looking for the length of a chord. That is perpendicular. That is a perpendicular distance of 5. So it's 5 some unit away from what? It's away from the center of a circle, and the circle has a radius of 8. So when you get questions like this, it's just usually piece by piece by piece, you draw it. All right, so it says find the length of a chord. So clearly we're dealing with a chord. Chords live on circles. So I need a circle. So it's find the length of a chord. So somewhere on this circle, I have a chord. And it says that chord is a distance of 5 from the center. So I could have drawn that chord as large or as small as I wanted, but I do know that it's 5 away from the center. Notice that 5 there doesn't go to the circle. It goes from the chord to the center, and we're told that it's perpendicular. Last, we were told the circle has a radius of 8. Now, some kids would draw it continuing from P to the circle and just label that part 3. You know, if it has a radius of 8, that means 5 plus 3 is 8. Other students would draw this probably knowing where we're going with this. So it says, find the length of the chord. So if we need the length of the chord, I need the distance between A and B. In other words, I need to find, either the entire thing or maybe pieces parts of it. I'm going to go for pieces parts. So I'm going to solve for either AP or BP. Notice it's a right triangle. I have 2 of the sides. Therefore, I can use Pythagorean theorem to find that third side. So I'm gonna find the distance of AP. So AB would be equal to 2 APs, right? And I just need one of them and multiply it by 2. So let's find AP. So let's see, Pythagorean theorem. So let's see, 8 is the hypotenuse. So 8 squared is equal to AP squared plus 5 squared. So let's see, 64. I got to subtract 25 from both sides. That leaves me with 39 and the square root of 39. There are no perfect squares that go into 39. So you get this really ugly answer here, square root of 39, but that's the answer for the distance of A to P. Now be careful. We didn't want the distance between A to P. We want A to B. And since we have that shape there, where it cuts the chord in half, then double that chord. So double root 39 would be 2 root 39. All right, one last proof. All right, third and final shape of the day, it's going to look like this. So let's see what this looks like. This looks like a circle, and it's got 2 chords. And then just like the previous problem there, it's got not a radius, but it's got a second segment that connects the chord to the center of the circle. And I've got 2 chords, so I've got 2 of those pieces. And we're told that those pieces, OQ and OP, are perpendicular to their respective chords, and they're also congruent to one another. In other words, OQ is congruent to OP. We're asked to prove if that's the shape you get, well, then the 2 chords, TU and RS, are congruent. All right, so that's the setup of the proof. Well, we've made triangles the last 2 proofs. How about we make triangles with this one? So let's make some triangles. So connect O to T, O to U, O to R, and O to S. There's our triangles. Clearly, we don't have vertical angles there. But since all the red lines are radii, then they're all congruent. So therefore, all the radii are congruent because they're radii. Well, we're already given that OQ is congruent to OP, so this one's going to be hypotenuse leg. So all 4 of those triangles that you see, the small ones, so all 4 of those triangles have to be congruent because of hypotenuse leg. And if all 4 of those triangles are congruent to one another, let's see, well, then that means that TQ is congruent to UQ. That means RP is congruent to SP, right? All of those little parts of the triangles are congruent. That's the black parts. And TQ plus QU is equal to the whole thing. Therefore, by the segment addition postulate, if we just add those together, TU is made up of the 2 smaller parts, RS is made up of 2 smaller parts. All the smaller parts are congruent to one another, and therefore, by a quick substitution, congruent segments have equal measurements. Therefore, the 2 chords are congruent. All right. So that's our last one of the day, and this is theorem 9.6. That's the shape you need to look for. So let's see. That shape is circle, 2 chords, and 2 segments that come from the center of the circle that are congruent to one another, perpendicular to the 2 chords. Okay. So that's the idea there. It is also biconditional. So if the chords are congruent, then the segments are congruent. And if the segments are congruent, the chords are congruent. Now, just be careful. The segments have to be perpendicular to the chords, and they have to come from the center of the circle. All right, one example to finish things up here. Let's see what we got here. Now, we got a circle. It looks just like that previous theorem where we have segments coming from the center perpendicular to the chords, and it says find the value of x. Find the value of x. All right, this one's a little bit tricky. We can't immediately say that QS is equal to 4 and be done with it, because in order for that to be the case, that means that UV has to be congruent to RT. The 2 chords congruent to the 2 segments. So we need to prove that first. So how do we prove that? If you just look at the right-hand side of that circle, that little cross-looking thing right there, well, that's from that previous theorem that says if you have a radius or diameter, it's perpendicular to a chord, then it cuts the chord in half. And since RS is labeled as 3, well, then that means ST is 3 as well. And if ST is 3, then that means RS plus ST is 6. And since the other side is 6, therefore the segment is 4. Now that seems like a circuitous way to get to the answer when it's obvious that it's 4, but that's the proof of why it's 4. You can't just immediately, just claim it's 4. Okay. So that's it for today. Lots and lots and lots and lots of shapes today, right? You may or may not have questions with your homework. If you do, as always, just send me an email and I'll get back with you within a few hours. And that'll wrap it up for today.